Every single transistor on your smartphone is now so small that you could fit millions of them on the head of a pin. But to print these features, engineers had to solve a problem that seemed physically impossible, creating a light source bright enough to etch patterns at the atomic scale. This is the world of extreme ultraviolet light, or EUV. It has a wavelength of just 13.5 nanometers, so short that it is absorbed by almost everything, including the very air we breathe. For years, the industry was stuck at a power output of 600 watts. But in February 2026, ASML shattered that ceiling with a 1,000-watt upgrade that changed the math of chip making forever. To understand why this power jump matters, we have to look at throughput. In a fab, time is literally money, billions of dollars of it. The brighter the light, the faster you can expose a wafer. Before this upgrade, the 600-watt source was the bottleneck. It limited how many chips a $300 million machine could produce in an hour, creating a massive backlog for the world's most advanced AI processors. By hitting the 1,000-watt milestone, ASML didn't just make the light brighter, they unlocked a 50% increase in wafer throughput. This means more chips, faster cycles, and a direct path to the next generation of computing. But generating 1,000 watts of EUV light isn't as simple as turning up a dial. In fact, you don't turn on this light at all. You have to create it through a process of controlled, high-frequency explosions. Think of it like trying to hit a falling marble with a needle from a mile away, except you have to do it 50,000 times every single second without ever missing. This is the plasma fire mechanic. It is one of the most complex engineering feats in human history, involving synchronized blazers, molten metal, and a vacuum more empty than deep space. To get to 1,000 watts, the engineers had to rethink the entire physics of the source. They weren't just scaling up, they were fighting the laws of thermodynamics. The 600-watt systems were already pushing the limits of material science. Moving to a kilowatt meant managing heat loads that would melt almost any other machine in existence. But the solution wasn't just better cooling, it was a complete redesign of how the light is captured and directed, ensuring that every single watt of energy is used with surgical precision. This is the story of how ASML's engineers built a star in a box. It's a journey through the extremes of temperature, speed, and precision that makes our modern digital world possible. In this video, we're going to dive deep into the hardware of the 1,000-watt upgrade. We'll see the laser that fires twice, the droplets that move like clockwork, and the hydrogen shield that protects it all. But first, we have to look at the fuel. It all starts with a single drop of molten tin, falling through a vacuum at 70 meters per second. Inside the light source, a generator spits out 50,000 droplets of molten tin every second. These aren't just random drops. They are timed with the precision of an atomic clock to meet a laser pulse in mid-air. Imagine trying to hit a raindrop with a laser pointer while you're standing on a moving train. Now imagine doing that 50,000 times a second without ever missing a single drop. That is the level of synchronization required here. The droplets are just 30 microns wide, about half the thickness of a human hair. If the timing is off by even a fraction of a microsecond, the entire process fails and the light goes out. The laser used to hit these droplets is a CO2 master oscillator power amplifier. It's one of the most powerful industrial lasers in the world, but it doesn't just fire once. It fires a pre-pulse and a main pulse. The pre-pulse hits the tin droplet first, but it doesn't vaporize it. Instead, it flattens the sphere into a perfect pancake shape, increasing its surface area so the next pulse can hit it more effectively. Just nanoseconds later, the main pulse strikes. This is a massive burst of energy that instantly heats the flattened tin to over 500,000 degrees Celsius, hotter than the surface of the sun. At these temperatures, the tin atoms are stripped of their electrons, turning the metal into a highly ionized plasma. It's this plasma that finally emits the 13.5 nanometer EUV light we need. This plasma fire happens 50,000 times a second, creating a continuous flickering star that serves as the light source for the entire lithography machine. But the plasma doesn't just emit light. It also creates a cloud of debris, tiny bits of tin and ions that want to coat everything inside the chamber, especially the mirrors. In the 1,000-watt upgrade, the intensity of this plasma fire is significantly higher. To reach a kilowatt, the laser has to deliver more energy per pulse, and the droplet generator has to be even more precise. The engineering challenge here is that more power means more debris and more heat.
If you just turn up the laser, you'll destroy the very mirrors you're using to collect the light. To solve this, ASML had to develop a way to manage 1,000 watts of raw thermal energy while keeping the internal optics perfectly clean. And the solution they found is a masterpiece of fluid dynamics. This is the collector mirror, a $300 million piece of hardware that is the largest and most precise mirror ever made. It is coated with hundreds of layers of molybdenum and silicon, each just a few atoms thick. Its job is to catch the EUV light from the plasma and reflect it into the rest of the machine. But remember, EUV light is absorbed by almost everything. This mirror only reflects about 70% of the light. The other 30% is absorbed as pure heat. At 1,000 watts of source power, that's 300 watts of heat being dumped directly into the mirror every second. Managing that heat is what makes the 1,000-watt upgrade possible.
In a vacuum, there's no air to carry heat away. This makes the vacuum chamber inside an ASML machine one of the most difficult thermal environments on Earth. It's like trying to cool a space heater inside a giant thermos. To reach 1,000 watts, engineers had to implement a high-velocity flow of hydrogen gas. This gas serves two critical purposes. It cools the internal components and acts as a physical shield against tin debris. The hydrogen atoms collide with the tin ions, slowing them down and pushing them into a catchment zone before they can ever touch the expensive mirror arrays.
But hydrogen brings its own set of problems. At high temperatures and under intense EUV radiation, hydrogen can become reactive, potentially damaging the delicate coatings of the mirrors through a process called hydrogen blistering. The 1,000-watt upgrade uses a proprietary gas curtain technology to keep the hydrogen at the perfect pressure and temperature, ensuring it protects the mirror without reacting with it. This is a delicate balance. Too little gas and the mirrors are destroyed by debris. Too much gas and the EUV light is absorbed before it can ever reach the wafer.
The result of all this engineering is a machine that can print 150 to 200 wafers per hour, a 50% jump over previous generations. This is what enables the mass production of the 2nm and 1nm chips of the future. When you look at your next smartphone or AI accelerator, you're looking at the product of this 1,000-watt star. It is the most precise manufacturing tool ever created by humanity. The transition from 600 to 1,000 watts wasn't just an upgrade, it was a fundamental shift in what is possible in the physical world.
Looking ahead, ASML is already working on the next milestone, high-NA EUV. This will use even larger mirrors and more complex optics to push the limits of physics even further. But none of it would be possible without the 1,000-watt source. It is the engine that drives the entire semiconductor roadmap for the next decade. As we push toward 1,000 watts and beyond, we are essentially learning how to control the power of a star to build the smallest things in the universe.
Next time you hold a piece of technology in your hand, remember the plasma fire. Remember the 50,000 droplets of tin and the $300 million mirror that made it possible. The engineering behind ASML's 1,000-watt upgrade is a testament to human ingenuity, a reminder that there is no limit to what we can build when we master the laws of physics. We've built a star in a box, and it's lighting the way to a future we can only begin to imagine.